Today we will be discussing about the summary of entire course lectures that we have discussed during these 12 weeks. Let us see the brief points which we are going to discuss. Started these pavement materials with the discussion of soil, then the aggregates and the bitumen. So what are the minimum properties that needs to be checked before using them into the pavement construction? Thereby then we followed with the mixed design of bituminous mixtures, where we have studied about the Marshall mixed design, superpave mixed design. Then we also have studied about the reclaimed asphalt pavement materials mixed design. Then how to do the mixed design. Followed by we characterize these materials as per the performance requirement. This is what as far as the bituminous mixtures are concerned. In addition to that, we also had a discussion on cementitious materials, GGBFS, and other slag materials, and also the types of cements that are available. Then we also had a discussion on concrete mix design. Island concrete mix design. Then we also have the discussion regarding the pervious payments mixed design. In addition to that, in very brief, in the last lecture, so we also have discussed about the alternative pavement materials instead of natural materials without compromising on the performance characteristics. So regarding all these topics, let us see a very brief discussion. Soil. So in the soil module, we have mainly discussed about the categories of soil. So if we see here, the categories of soil is mainly depending upon the way how the soil has been formed. We know that the soil has been formed due to the disintegration of rocks. Of rocks could be at one place or it could be transported to some other place, and during this transportation it can be either transported through air, or it could be either transported through water, or it could be either transported through snow. So there must be various modes of transportation. So if that soil is disintegrated at that place, that was called as residual soil, and if it is transported to other places, that is we called as sedimentary soils. So these sedimentary soils are further named based upon the medium, like if it is through the medium of river, glaciers, lakes, then we have the designated category of soil. So we know that from a bigger cobbles or gravels, boulders, to the smaller size, it happens due to the disintegration, and we have finer and very finer soils which we call as silt or clay. So how do we distribute these sizes? So once after the categories of soils has been finalized, we need to distribute these particles into different sizes. So if the particles are of bigger size, we could do this using sieve analysis. So for example, boulders, gravels, till sand, and silt. We can categorize these aggregates using sieve analysis. For example, those soils which are fine in nature, let us say whose size is less than 75 micron, those soils actually they stick to each other. Even if you try to sieve on a sieve, what happens that those aggregates are not separate, so they would be stick to each other. Either they will be sticking to each other, those particles, otherwise those particles would be sticking to the surface of the sieve. So clay is one of that kind of soil. That is the reason why using sieve analysis we cannot able to determine or classify the particle size of the soils. Thereby, for those soil particles whose size is less than 75 micron, we have not performed sieve analysis, hydrometer analysis. This hydrometer analysis was mainly based upon Stokes' law. If we could recall what was the Stokes' law, so if we have any particular particle, let us say this particle which is mentioned here of diameter capital D, let us say. So if I have mixed all the soil particles with some kind of solution, and if I could have waited for a particular amount of time, let us say T, so after a particular amount of time T, few of the particles will be settling at the bottom. Those who has the higher specific gravity or density, they would be settling at the bottom. Those which are smaller than this size, they would be still at the top. So after particular amount of time T, so some percentage of the particles are finer. So let us say these red particles are finer than some size capital D. We do not know what was that. So how does these particles would be settling? With time, what happens? Sometimes 2-3 particles would be agglomerated together. They would be slowly settling to the bottom. So this is due to the difference in the gravity or density between the medium. Here the medium, let us say, is water, and the particles are having different density. So in order to determine the density of two different particles who are having differences in their density, we usually follow the Stokes law. Using this Stokes law, so hydrometer analysis can be performed. For example, now we have a soil particle. For the soil particles which are of the size less than 75 micron, we will be adding the dispersing agents. So this dispersing agents, the purpose is it will not allow the soil particles to flocculate or agglomerate together. So it will make the particles to be away from each other. So we will be mixing the dispersing solution. After mixing, we will insert this hydrometer into that solution. So once after inserting the hydrometer into the solution, we can see there are few readings on the top of the hydrometer. After a repetitive amount of time, let us say after 1 minute, 2 minutes, 4 minutes, 8 minutes, after particular amount of time, we try to note down the readings of the hydrometer. These readings would be changing with time, because we could observe that with time the relative density of the particles would be increasing, thereby they would be settling at the bottom. So this is the main process to determine the sieve analysis of fine aggregates. So in the sieve analysis of fine aggregates using the hydrometer, the main output which we would be observing is the capital R, which is the reading on the hydrometer. So this hydrometer reading needs to be corrected for three corrections. One is the meniscus correction, another is the temperature correction, and another is the small d, which is for the dispersive aging correction. What is for this meniscus correction is, for example, if you dip the hydrometer into the water, exactly water would be like this, so hydrometer will be dipped like this. But if you dip in the solution, you could observe that there will be a rise in the, you can observe this as the meniscus. So that means the actual reading is this, but you are observing reading as this. That means if you see the hydrometer reading, here 5, here 6. So your actual reading should be 6, but you are observing it as 5. That means you are observing reading as less. So you have to increase that, because actual reading was 6, but you are observing it as 5, so you have to add. That is the reason why meniscus reading is always positive. In the similar way, if you look at the temperature, what happens? Whenever we increase the temperature, density would be reduced. If the density is reduced, let us say I have inserted the hydrometer into the beaker. Now its position is here, this is the reading. If the density is less, that means the solution is very light. In that case, what happens? This hydrometer would be sinking more. So when it is sinking more, the reading would be at top. Reading is at the top means that is at the lower value. So when the reading is lower value, we are supposed to increase it. So if the temperature increases as the density decreases, the correction for the temperature would be positive. But if the temperature is decreasing, then the correction would be negative. In the similar way, for dispersing agent also, if we add the dispersing agent, what happens? Density would be increasing. So if we have normal water, if we add salt to that, what happens? Density of that water would be increased. In the similar density of the water would be increasing. If the density is very high, then hydrometer would be floating. It will not be sinking. If it is floating means its value would be at so lower value. So for example, one is the expected reading, but two is what you can see because it is floating. So two means it is a higher reading on the hydrometer. That means higher value, but the original value is lower. So you need to reduce. That is the reason why dispersing agent correction would be always negative. So using this hydrometer reading, one is you can calculate the specific gravity of the different samples. Another is we can also calculate the percentage final. As I have discussed, after particular amount of time, I told that some amount of the particles will be final. So how much amount of that will be final? That can be determined using this. If we could see this formula, we know the corrected hydrometer reading, and also we know the weight of the soil that we have already mixed into the solution. So these are the three main things that we can observe from the hydrometer analysis. So from the sieve analysis on the coarse aggregates which are greater than 75 microns, so two outcomes would be coefficient of uniformity Cu which is D60 by D10 and also coefficient of curvature Cc which is D30 square by D60 into D10. So this D60 and D10 are the, for example, when I say D60 is equal to percentage of the particles are having size lesser than 2.3 mm. So in a similar way, we can understand remaining sizes description also. Soil chapter, another important discussion we had done was consistency limits and the classification of the soils. So if we could remember, uh, we have the soil. Let us say the soil is mixed with water. So when the water is very high, let us say, so we haven't dried that soil. Water is in liquid state. That means it is very sloppy and flowing in nature. So from that state to the plastic state, that means now it is slowly getting solidified because we are removing some of the water through evaporation. So after particular amount of water limit, the soil state would be changing from liquid state to plastic state. That is what we call it as liquid limit. So this we have observed using a bowl. So we have taken a random soil sample which is passing through 425 micron and we have added some trial water content. Then we have placed the soil paste into this and we made a cut over this and we tried to give some blows to this. So then we have drawn a corresponding graph number of blows versus the water content. So the water content that is corresponding to the 25 blows is what we consider it as a transition water content from liquid state to plastic state. So that limit or that water content is what we have named it as liquid limit. In the similar way, now I have evaporated few of the water from the soil. If I further remove some amount of the water, then soil state would be changing from plastic to semi-solid. So that transition stage water content we call it as plastic limit. So how do we determine at what water content this would actually turn from plastic to semi-solid is using a thread. We take the soil sample again, we add a random amount of water, we try to make 3 mm of thread. So when we are making thread, if you could see crumblings or cracks on that soil thread, that was the water content at which soil would be changing from plastic to semi-solid. And if we further reduce the water, soil state would be changing from semi-solid to solid. So this transition stage is called as shrinkage limit. One from liquid limit to plastic limit to shrinkage limit, we can see that here the volume is very high, volume is keep on reducing. But if you see in the shrinkage limit, if you further even reduce the water also, there will not be any volume. So water content at which there is no change in the volume of the soil water paste. So why do we even need to determine these consistency limits is because now we wanted to classify the solids, but because based on Cu and Cc values for coarse aggregates we have already classified them as either they are well graded, poorly graded or uniformly graded, or whether they are gravel because Cu is greater than 4 and Cc is 1 to 3. If Cu is greater than 6 and Cc is 1 to 3. So based on these values, we have already classified the coarse aggregates. If I wanted to classify the fine aggregates, then we have a chart which we can see it here. This chart is from liquid limit to plasticity index. So this plasticity index is nothing but the plasticity index would be the difference between liquid limit minus plastic limit. So we need the liquid limit and plastic limit so that we can calculate the plasticity index, and we already have the corresponding liquid limit. So based on these two, we can actually classify the fine aggregate into either they are low compressible soils, whether they are highly compressible soils, or whether they are intermediate compressible soils. So whether they are low, high or intermediate, the boundary is based upon the liquid limit. If the liquid limit value is less than 35 degrees, that means that is called as the low compressible. If it is in between 35 to 50, that is called as intermediate compressible. And if the liquid limit is more than 50, that was called as highly compressible. Even after determining whether they are low compressible, high compressible or intermediate, we also have to determine whether they are clay or silt or organic samples. So to determine that, we need to take the reference of plasticity index. IP equal to, if you could see here, 0.73 into liquid limit minus 20. So as per their classification, this is the IP line. So here we can actually calculate our plasticity index as liquid limit minus plastic limit. So if our plasticity index falls below this, then we can consider them as either organic or silt. M means silt, O means organic. If our plasticity index falls above this, then we can consider them as clay. These are the two types of information that we require to classify the soils. So in addition to this preliminary investigation, we also have studied about the strength properties of soils. So to understand the strength of the soil, initially we have studied about their compaction characteristics, standard compaction, modified compaction, and we have different mold dimensions and also number of blows, number of layers to be filled based upon the either we are going to do standard or modified Proctor test. And also if I wanted to understand the strength of the soil in the field but not in the laboratory, then we also have core cutter method and also standard sand replacement method. In addition to these compaction characteristics, we also have studied about shear strength characteristics. So to understand the shear strength test, we have studied one is direct shear test, triaxial test and unconfined compressive strength. The concept in all these tests is we will be applying a vertical compressive stress on the material. So when we apply this vertical compressive stress on the sample, so we know that when a vertical stress is applied, there will be a shear plane or weak plane that will be formed through which material is going to fail. If we have a confinement from the surroundings, material will not be failed immediately. If there is no confinement, it will be failed immediately. So in the unconfined compressive stress, we will be using zero confinement. In the triaxial, we will be using more confinement. So this direct shear test is, we will be fixing the specimen the bottom part but we will be applying a load in the top part. So we will be observing at what normal stress, at what horizontal stress usually material is going to fail. So if it could able to take more stresses, then we can determine that as a strength soil. In addition to the strength of the soils, in order to understand the stiffness of the material, that is nothing but the modulus of the material, we also have performed resilient modulus test. This resilient modulus test can be performed on either soils and also on granular materials especially. So what is this resilient modulus test? We know that initially whenever we apply a load on any specimen, it will undergo some deformation. That means strain will be keep on increasing. So after some time what happens? Some of the strain can be recovered, but after if I apply load again, then you can see that there will be still accumulation of strain. Again there will be another accumulation of strain. So after particular amount of n number of cycles, whatever the permanent deformation or plastic strain that is going to develop in the soil, that will becomes constant. So after that means if you take the soil and if you keep on applying a compaction using a roller compactor, let us say a roller is rolling on the soil, after let us say 100 passes, soil becomes very stiff that even after that, even if you are allowing so many passes, there is no chance for the compaction because whatever the voids available, you have already compacted and everything was done. Then after that, material starts behaving as a elastic material. So there will not be any deformation. Even if there is any deformation, that can be recovered. So that recovered deformation is what we consider that recovered deformation, and that time what is the stress I am applying, that ratio we use to calculate the modulus value, that is what called as resilient modulus value, or we can also call it as elastic modulus value. Usually for granular materials it is completely difficult to understand the plastic deformation characteristics, that's why we assume this resilient modulus as the elastic modulus and we calculate the value. So, and also if there is already constructed pavement and if I wanted to understand what is the strength of the subgrade at the bottom, then we have dynamic cone penetration test and also plate load test to understand the field performance. And for the same soils, if I wanted to understand whether it has higher amount of clay content than the recommended specification. So how do we understand that? That using the pre-swell index, we can take some amount of soil, we add kerosene to that and also we add water to that separately. Whenever there is a water, these soil particles would be absorbing water, its volume would be increasing. React with the soil. So whatever the amount of change in the volume due to the interaction with the water, that it represents that there is a higher amount of clay content in the soil. So this is the these are the main points in the soil module. And if we come to the aggregates chapter, in the aggregates chapter, mostly initially we have started discussing about the formation of rocks or aggregates. For example, igneous rocks, how they have formed from the lava when they get solidified. And those igneous rocks, when they have disintegrated and they have moved from one place to another place, they have been converted into sedimentary rocks, and those sedimentary rocks under the pressure and also the temperature, they have been transformed into metamorphic rocks. These are the rocks which further disintegrated and converts into the soil. So before converting into soil, these rocks are actually formed from the earth crust. So on these aggregates, before using them directly into the pavement construction, we have discussed about few of the aggregate tests that needs to be performed so that implies a higher strength can be achieved during the traffic loading. So one is main is the flakiness and elongation test. We do not want our materials to be very flaky. That means we do not want them to be very thin, and also we do not want the material to be very long because under the load application they will break. Once they get broken, what happens? Initially we might have some aggregate gradation. We could have added some binder and we have achieved some voids and volume. If the aggregates are of very long and thin, they may get broken, then their sizes would be changing. If their sizes changes, their gradation would be changing. Changes, their volumetrics would be changing. So your VMA values, air voids, and the voids filled with bitumen, all the calculation which we expected will not be seen in the field. So, and too thin, and also to avoid the crushing of the aggregates, we also have performed the impact test and also abrasion test using Los Angeles abrasion and some other equipments. And we have also determined the surface area of the aggregates. This surface area was calculated to understand the bituminous film thickness. We know that fine aggregates should be having higher surface area, thereby it requires higher amount of binder to coat them. So based upon the surface area, if calculate the bituminous film thickness. Thereby, we can actually differentiate between the dense and also gap graded mixes, where gap graded mixes have the more probability of having higher film thickness, and also dense graded mixes with lower film thickness. This film thickness actually indirectly required to understand the moisture damage of the asphalt mixtures, because having lesser film thickness would cause to higher water damage. And one of the important aggregate tests that we have discussed is the specific gravity. In the specific gravity, three main specific gravities that we have discussed was bulk specific gravity, apparent specific gravity, and effective specific gravity. And we also have discussed that it is experimentally difficult to calculate the effective specific gravity in the lab, because let us say if this is the aggregate. So if somebody asks what is the volume of the aggregate, we need to if somebody asks what is the volume of the aggregate, we need to measure these boundaries to calculate the volume. But this is not a regular shape. So in those cases, nobody could be able to measure what is the volume of that. Then how do we actually calculate its volume? So that is one of the difficulties. If at all, if I consider only this volume, without soaking into the water. That means I have kept my aggregate material into the oven. Then I have completely dried for 24 hours at 110. That means there is no water inside. So whatever the weight I am taking, that is the weight. And the volume, whatever that replaces my dry aggregate, that is the volume. So if I consider that is called as apparent volume. So that specific gravity, whatever we calculate, could be apparent specific gravity. So, but take that we wanted to consider this entire total volume. That means the voids whatever present, we also wanted to include that. That means this volume 2 is, specific gravity is weight by volume. So when V2 is more means G will be less. That is the reason why bulk specific gravity will be less, apparent will be more. But if I wanted to calculate the effective specific gravity, what is the effective specific gravity? In the bulk volume, we are considering all the voids and also aggregate. In the apparent specific gravity, we are considering only aggregates. So what is the reality? In reality, there are aggregates. On the aggregate surface, some small pores would be there. So in that pores, binder can be entered to some extent. It may not be entered into full pores, because based upon the viscosity. If the viscosity is very less, the binder may enter into the bottom of the air voids of the aggregate surface. Sometimes it cannot. This is the air void. This is the void. In that void, we observe that only till this portion bitumen could able to enter. Whatever the remaining portion here, bitumen could not able to enter. So if somebody asks what is the volume of the aggregate, that portion that is not filled with bitumen. So that one, and also this real aggregate. So whatever this outer surface, this is really the effective volume of the aggregate. So in order to understand this volume, we need this. What is the amount of binder that is being absorbed onto the aggregate surface? But nobody can understand how to calculate the amount of bitumen that is being absorbed by the aggregate. We do not have a procedure for that. That is the reason why experimentally we cannot calculate the effective specific gravity. But based upon the apparent and also bulk specific gravity and also theoretical specific gravity GMM, we have the formulas to calculate the effective specific gravity. These are the three specific gravities usually we use. Mixed and volumetrics are mostly depending upon the bulk specific gravity, theoretical specific gravity, and effective specific gravity. That is the reason why we need to be more conscious in calculating the specific gravity. In the third chapter, we have discussed about all bitumen related properties. So, mainly bitumen, tar, cutback, and emulsion. So, these are the four kinds of bitumens, I should say. Bitumen is a pure bitumen that I have not processed and I have not done anything extra, which we usually obtain from the fractional distillation of the crude oil. So we have the crude oil with us. We are subjecting this crude oil to particular atmospheric pressure at one stage. Then later we will be again subjecting them to vacuum at another stage. So at the end, whatever is the residue that is remained, that we are calling it as the bitumen. So sometimes let us see whatever there I have observed is BG30, and if somebody asks for the stiffer bitumens, that means I wanted to produce let us say BG40. So there are processes using air blown method or de-asphalting. So there are methods using which we can actually produce higher stiffness binders than the residue that we have received. So whatever may be the stiffness, whether it is higher or lower, all the bitumens are actually consisting of four fractions which are called as Sara fractions. So this is what about the bitumen. In the similar way, tar is a material which is not obtained from the crude oil. This is actually obtained from the wood or charcoal. So this has to be done in the presence in the absence of oxygen. We will be burning the coal. Then whatever the end product would be obtained is the tar. It actually releases harmful gases into the environment. That is why the usage of tar has been eliminated from so many years. And another type of bitumen is cutback. For example, I have produced VG40 bitumen, but it is very stiff. If I wanted to heat this and also mix with the aggregates, I have to meet this bitumen to higher temperatures. But we do not prefer using higher temperature means I have to produce higher, I have to use higher energy. That is the energy consumption. If at all I wanted to decrease the viscosity so that I can easily mix with the aggregates, but I do not want to heat the bitumen. Cases, cutback is another type of bitumen. That means we are converting the bitumen into another form. So we will be adding some solvents like kerosene, naphtha, and other solvents. So temporarily, bitumen would be reduced. It's reducing to lesser viscosity. After coating to the aggregates, whatever the solvents that we have used, for example, if I use diesel, it will evaporate quickly after coating the aggregates. Then kerosene. So based upon the type of the solvent I have used, they may get evaporated. Then we also have named that if they evaporate quickly, that is rapid curing. If they evaporate slowly, that is slow curing. So we have specifications for that. In addition to that, I do not want to add any solvents because I was telling that after particular amount of time, these solvents would be evaporated to the environment. That means we are actually making diesel to release into the environment, kerosene to release into the environment, which is not suggestible. So in those cases, if I do not want to make that damage also, then we go for emulsion. So our main purpose is to reduce the viscosity. So how do we do? Now we have bitumen. This bitumen is very stiff. So to very stiff materials, if we wanted to make into soft, first option would be we have to crush it, make into small pieces so that they can be made into less harder material. So what can we do? We can use some high shear equipment. So using high shear equipment, that equipment will be used to make the bitumen into small particles. But will this reduce the viscosity? Because after some time, what happens? Heat to some particular temperature, then we apply the shear so that they will be converted into small particles. But immediately after some amount of time, they will come close to each other. So what happens? Then we have to use some other phenomena. That is what the phenomena in emulsion that we will discuss in the upcoming slides. So these are the four kinds of bitumens we are going to use. In all these bitumens, the main fractions which I was mentioning are Sara fractions. saturates, aromatics, resins and asphaltenes. In these Sara fractions, resins and asphaltenes, these two are the polar materials. Polar material means in their molecular structure, they have some heteroatoms like nitrogen, sulfur, and oxygen. So, what is the use of that? If they have these, actually they can react with anything else, each other. Like resins to asphaltenes also they can react. So they are not like inert materials. They can react with environmental products. They can react within themselves. If I am going to add some polymer from other outside to increase its properties, still they can react with them. But saturates and aromatics, these are actually non-polar materials. They do not have heteroatoms like this, so they will not be reacting. Then what is their purpose is these first two saturates and aromatics, they are like some medium. So they provide a home for the resins and asphaltenes. So these resins and asphaltenes they will be floating in a medium. That medium is actually provided by the saturates and aromatics. So based upon the concentration of saturates and aromatics, based upon the concentration of resins and asphaltenes, all the stiffness and their chemical properties, their aging behavior, elasticity behavior, all those will be dependent. So how do I know if a bitumen is given? How much amount of asphaltenes are there, saturates are there? That is based upon the chromatographic techniques. We have SARA test. So we have exclusive equipment to extract the amount of all four components. So these are the chemical analysis. In addition to that, if we want to further understand the bitumen, we have consistency tests like penetration, softening point, viscosity, and ductility, and durability test. Durability is that means how far this bitumen could able to serve the field conditions. So this is especially with regard to the aging. So when it is not aged, when I say aged, that means I have the bitumen. If this bitumen is exposed to oxygen, it will react with oxygen. So when it reacts with oxygen, what happens? So sometimes whatever the lighter oils present in this, sometimes they may evaporate. Sometimes, so these resins and asphaltenes, because they are polar, they will react with this oxide. For example, sulfur is there. When it reacts with oxygen, they may create some sulfur related oxides, nitrogen oxides. So they will actually react and produce new oxides. Now, previously there is just asphaltene. Now in that asphaltene, some oxides are added. What happens if some extra material is coming and adding? Its density or specific would be increased, thereby material becomes very stiffer. That is the reason why once the material is getting aged, it becomes more stiff or strong in nature. So if we wanted to understand whether the behavior of the material is how far it has changed, we need to do this durability test, that is aging test, and purity test. So after this distillation process, whatever the bitumen I have observed, that bitumen if I could able to dissolve in trichloroethylene or carbon disulfide, so I should not observe any residue on the top. So it should be completely dissolved. So that is what the purity test, and also the safety test. This is flash and fire point test. We have discussed that. So sometimes when bitumen is being heated, few of the fumes would be coming out. Those fumes would be catching the fire immediately. So we need to understand at what temperature fumes would catch the flame, so that we have to avoid heating the bitumen to that temperature. That is for the safety of the user. So flash and fire point test would be used to understand that behavior. In the durability test, not just the aging, the steric hardening. So as I have discussed, in the Sara fractions, resins and asphaltenes, both of them are polar in nature. That means it also has nitrogen, sulfur heteroatoms. It also has nitrogen, sulfur, oxygen heteroatoms. So even at room temperature, let us say 35 degrees also, these two will be reacting with each other and they will form these oxides, and bitumen becomes more stiff even without heating, without exposing them to oxygen also. But still, this is a temporary process. So once, usually whenever we are going to use the bitumen, initially we heat it. because if I want to do penetration, I have to heat and pour into that. So during this heating process, again they will be going back into its original condition. So this condition is actually called steric hardening. This steric hardening can be removed with heating of the bitumen, so that is not a problem to the bitumen. And another concept regarding bitumen that we have discussed was the viscoelasticity. So we know bitumen is not just a viscous material, not just elastic. It has the properties of both viscoelastic, viscous and elastic at what temperature? Let us say if you take the intermediate temperature 25 degrees, so bitumen may behave like a elastic in nature, but higher temperatures greater than 135 degrees, bitumen will be very fluid in nature and it may behave like a viscous. But in between temperature that is less than 90 degrees and 25 to 90 range, so this is the range where actually we compact the asphalt mixture in the field, and also the 60 degrees summer temperature. These are the temperatures at which bitumen actually behaves with viscous and also elastic nature. That means when the load is applied, immediately there will be some deformation. This is because of the elasticity. Then there will be still deformation. That deformation will keep on increase with the time. So after some time, if I have removed, some of the deformation will be recovered. But recovered. To recover fully, this is a time dependent recovery. So this is nature. This is due to the elastic nature. At the end, whatever the amount of time you give, if you could observe on the road, there will be depression on the top surface. Even if you allow for 100 years, that depression will not be coming into the original position, because that is called as plastic deformation or permanent deformation. This is due to the viscous nature of the bitumen. So bitumen has elastic, viscous and also viscoelastic nature. So in order to model this behavior, for example, I have a binder. By now we already know dynamic shear geometer test, creep and recovery test. If I could have applied creep and recovery test onto the bitumen, so it will have some amount of creep, some amount of recovery would be observed. So I wanted to understand what is the percentage of elastic nature, what is the percentage of viscous nature, how much is the viscoelastic nature. We need to quantify, so that if I have four different types of binders, I can actually characterize which binder is more elastic, which is more plastic, which is more viscoelastic. In order to quantify that, the data that we are receiving from the this creep and recovery experiment, that needs to be modeled. So in order to model that, we have one is Maxwell model, Kelvin model. In the Maxwell model, so we know this is the dashpot, this is the spring. Spring represents the elastic nature, dashpot represents the viscous nature. So if these two are in series, that is called as the Maxwell model. If these two are in parallel, that is called as the Kelvin model. But we have already discussed there are few disadvantages in the Maxwell and Kelvin model. It could not able to capture this time dependent recovery, and also in the Kelvin model also we could not able to see this initial elastic nature. Thereby, by eliminating the limitations of this both Maxwell and Kelvin, we have suggested something called as Burger's model. So in the Burger's model, this is a Maxwell, this is one Maxwell element and also one Kelvin element. We kept them in the series and then we tried to fit our model data into this model. If it could able to simulate the data into this model, then based on that we can calculate the parameters. For example, if you could see here, beta, there are slope of these curves. All these things represents the behavior of the material. So sometimes what happens is that even though we try to fit our data into these models, we could not able to really understand the viscoelastic nature of those materials, because nowadays we have all modified bitumens and also different test conditions. So those might not be in the linear viscoelastic regime. Those models that we have discussed are only when the material is in linear viscoelastic range. But we know that the traffic conditions are beyond our expectation now. Bitumen might enter into the nonlinear regime. When I say nonlinear regime, their stress and strain are not proportional to each other. So you cannot say, for example, I have applied 2% of the strain. 2% of the stress. So I expect that the same proportion of strain. It will not happen because of the nonlinear behavior. In those cases, what we do is, so generalized model. For example, we already have a Burgers model. To this Burgers model, we try to add these Kelvin elements. For example, initially I will add one Kelvin model. Then I will see whether my data fits into that. If not fitting, add another Kelvin model. So we keep on adding to the Kelvin model so that at some point our data would be fitting into one of the model. Thereby we formulate the equation and we say that my binder behaves in this form. So that is our rheological model. And in addition to that, we also have discussed about the grading of the bitumen. So previously it was penetration grade just based upon the empirical test. Then currently we are in the viscosity grade in India, whereas in other countries we are using performance grade system. We know at 25 degrees, that is intermediate temperature, and also at higher temperature. For testing at intermediate and high temperatures, we use dynamic shear rheometer. But to test at the mixing and compaction temperature, usually we use rotational viscometer. So because at this temperature, a binder would be Newtonian in range. That means Newtonian is exactly like water. Let us say it stress and proportional to strain. So stress is or modulus is independent of the strain rate. So in those cases, we can use rotational viscometer. This bending beam barometer is for low temperatures. In India, we do not categorize or characterize the material for low temperatures because we have a lesser chances of low temperatures. So in addition to this original binder, we have modified binders because due to this excessive loading conditions and also we wanted to utilize some waste materials into the bitumen, considering the environmental sustainability and all those things. We are now using most of the modified bitumen so that because we have intermediate temperatures, we have high temperatures, we have compaction and mixing temperatures. We want the bitumen to perform better in all ranges of temperatures. It was mainly impossible for the unmodified binders to be effective in all these temperatures. Polymers or crumb rubber in such a way that at low temperatures they will behave like elastic in nature and they will not crack, and at higher temperature they will behave in a stiffer manner, they will not rot. So how do we quantify initially before using them? One is the elastic recovery, how much elastic they are, and another is the storage stability. So if I add some external polymer into my binder, that polymer should not be separated from the original binder, that can be confirmed from the storage stability. And also another test that actually confirm the characteristics of modified bitumen is the multiple stress creep and recovery test. So these are about the regular bitumens. So as I was discussing about emulsion previously, so to the bitumen, we heated to let us say 130 degrees and we have applied high shear. Then my bitumen has converted into small particles. But after a few times, what happens again? Those particles will come closer. Then again, viscosity will increase. Then there is no point of like applying this high shear. So I want this material to be away so that when aggregates comes in contact, this will be coated onto the surface of each other. So one of the ways, let us say, I have a bitumen particle, small particle, small particle, small particle. When will they be away from each other? If they have same charge, let us say all are positive charges, then they will repel from each other. But how do we actually make their surfaces with same charge? That is when we use something called as the emulsifier. So if you could see here, emulsifier looks like this. Okay, it has a head and tail. So immediately when the bitumen is broken into small pieces due to the high shear blending, we add the emulsifier. So that emulsifier will come and it will coat the surface of the small bitumen particles. So this is one bitumen particle, this is another bitumen particle, this is another bitumen particle. Now you see all the bitumen surfaces are coated with the emulsifiers. Once they are coated, what happens? Now all the bitumen particles are they will repel each other. So you may say that then if they are always away from each other, that will be problem when we mix with the aggregate mixture. So this is a temporary. For example, once if I mix with the aggregate, usually these bitumens are now suspended in some medium. There must be some medium. So when these small particles are provided after high shear blending, in addition to this emulsifier, we also add water. So currently, small particles of bitumen are floating in the water. They are floating because their surface is charged with the emulsifier. Once if I add aggregates into each other, will be coated on aggregate. Whatever the water that is there, that water will be evaporated. Once the water is evaporated, that is what we call it as breaking. So this emulsion process will be broken when that water gets evaporated. How do we know? Initially, when I add this emulsifier and water, bitumen looks like brown in color. Once this breakage happened and water gets evaporated and all the bitumen gets coated on the aggregate surface, this brown converts into black. We know black is only bitumen. There is nothing else added. That's when we say that emulsion has been broken. So this is one of the way we use to reduce the viscosity. So after the bitumen, we have studied about the bituminous mixtures mix design. So the main strength of the bituminous mixtures is shear strength. So when the load is applied, compressive stress from the top. So when there is a support from the bottom, that support will resist. If there is no support from the sides, material will try to go away to the sides. That is what we call it as it is weak in the shear in that direction. Thereby, it will fail in that direction. So based upon the shear strength of the aggregates, if the aggregates are completely interlocked, then they will not be failed so quickly. So aggregates provide the main shear strength. Though aggregates are mainly interlocked and providing the high shear strength, there should be some binding method in between the aggregate so that that keeps aggregates together. The complementary bonus strength that is provided by the binder. But as far as the asphalt mixtures are concerned, shear strength is provided by the aggregates and the shear strength is being supported by the binder. So whether that binder is very steep or if it is very flowy, this all depends upon the viscoelastic nature of the binder. That is the reason first we characterize the binder, we understand the viscoelastic behavior, its temperature susceptibility. Then we study about the aggregates and its shear strength properties. Those aggregates that are good at its shear strength, very good with the durability and temperature susceptibility. We both of them and then we prepare the mixture. And this mixture again now we will test for vertical compressive stress is what I apply. When the vertical compressive stress is applied, how the shear stresses are formed, how the tensile stresses are formed at the bitumen. So this is the asphalt mixture slab. Let us say if I have created. So this is the vertical stress I am applying. There will be a resistance from the bottom. That bottom can be soil subgrade or anything. There can be a resistance from the side, that is a confining pressure. So as the load is increased, there is a chance that this can bend. Then there will be some tensile stresses produced at the bottom. There can be compressive stress at the top. These compressive stresses will lead to the one is rutting and sometimes the top down cracking. This bottom, they will be causing bottom up cracking. That is, crack will be initiated here and it will propagate into the top. So this is what we call it as the fatigue. So fatigue and rutting. These are the two main distresses that we observe on the pavement. So any mixture that we are producing should be having the capacity to resist the vertical compressive stresses and the shear stresses and also the tensile stresses at the bottom of the HME. This is what usually we check in the pavement design. So before going to the pavement design, we characterize the materials. We take the properties like resident modulus of the materials. Then we use those materials properties and then we check for these stresses. If the stresses are less than the whatever the stresses that are produced from the vehicular load, they should be lesser than the strength of the material. So in that case, we can say that we can use this material. So for doing the mixed design, we collect different sizes of aggregates so that we have dense packing. Then we characterize the binder. We calculate the mixing and compaction temperature so that they can coat the aggregates well. Then we prepare the bituminous mixes. Let us say if I am doing Marshall mix design, then I prepare the specimens. Then in the specimens, I calculate the volumetrics, the what are the air voids in the mineral aggregates, because all this actually recommends its behavior in the upcoming years in the field. Then those samples I will check for either stability. If I am going to check for performance, then I will check for rutting and fatigue. Then at the end, if everything gets satisfied, then we say that this is the final mix design. So very briefly, let us see what are the main points that needs to be remembered. We know this is the structure of the mixes where we have aggregates, then also binder that is being absorbed. Then there is some binder that is still available on the surface of the aggregates, in between the aggregates, that is called as the effective bitumen. So this effective bitumen and also absorbed bitumen together is called as the total bitumen. Then we have air voids. So these air voids, we need to make, we should not have very less air voids, because we have discussed in the summer, if this bitumen actually wants to expand, definitely it will expand because temperature will increase. Then it should have a sufficient space to expand. If there is no space, that bitumen will come to the top. Especially when it is about to expand, but vehicle also moves on the top surface of the bituminous mixture, bitumen will be coming out. That is what called bleeding. That problem will be observed. So we wanted to have some designated air voids, total bitumen content, and also voids filled with bitumen. So these are the few of the formulas that we regularly use. So we do the mix design of hot mix asphalts. Let us say in the hot mix asphalt, we were using only the virgin aggregates. In addition to that, if I wanted to use recycled aggregates, how do I do the mix design? So now you have virgin aggregates plus you wanted to use some wrap aggregates. So you have virgin aggregates, you wanted to use some wrap aggregates. So wrap already has some binder. So because of that, wrap is actually very stiff in nature. Now I do not want very stiff mix, but initially it has to be soft, because being too stiff is not good for fatigue again. So, and also the binder content that is present on the wrap, that might not be sufficient for the mix design. We need to add some extra binder. So when I wanted to add extra binder, what grade of bitumen I have to add? That is one thing. What amount of bitumen I have to add? Which type of viscosity I have to choose? Those are the unknown things. So initially, if I have a wrap, I have to initially determine what is the binder content that is present. Either using ignition woven method, that means we heat the wrap aggregates. Initially we take the weight, then after that we heat the material for more amount of time. Then we see what is the loss of the binder. Then again we further keep heating. At the end, we make sure that all the binder is evaporated or filtered. So then at the end we will take the weight of that wrap. So the difference is what actually the binder content, that is one way. Another way is the solvent extraction method. We actually dip these aggregates into some solvent. So that solvent actually dissolves all the bitumen present on the wrap. So initial weight and final weight we will take. Whatever the loss in weight is nothing but the binder content. So based on either ignition method or solvent extraction method, initially we calculate what is the amount of binder content that is present. So if I wanted to have 4% air voids at the end, so then what is the total bitumen that needs to be added? That can be determined. For example, after determining the binder content in the wrap, whatever the aggregates remain, that can be done for gradation. So you will do usual gradation, then extra binder that needs to be added, that we determine. So when we extracted bitumen from here, we can perform the viscosity test at 60 degrees. So based on that, we know we can actually give a grading to that, either it is BG30 or 40. So now when I wanted to add some extra bitumen, new bitumen, whether I should add any bitumen that is soft wrap the stepper. That how do we determine that? So initially, let us say if we are replacing 15% of the wrap out of 100%, if my wrap is 50%, you don't need to change any binder content. You can actually use, because you are not adding too many new aggregates, too much of wrap percentage. So whatever the binder content that is present, that you can use. But if your wrap percentage is more, let us say 15 to 25%, we need to use a binder grade that is one grade lesser than the usual. And if the wrap percentage is 25%, you cannot directly decide. We have to use the blending charts. So blending charts, when I say, for example, now wrap is 25% more. So I have to add the new binder. Then what is the viscosity of the new binder? What is the type of the binder? What is the greater than 25% means it can be any percentage. Blending charts. Otherwise, for less than 25%, we do not use the blending charts. That is for the wrap mix design. If you look at the cold bituminous mixes, so as we have already discussed, we have discussed about the emulsion. So why did we even come for the emulsion? Because we do not want to heat the bitumen to very higher temperature, but still we want the bitumen to have lesser viscosity so that it can coat the aggregates very quickly. In the same way, I do not want to heat my binder or aggregates to higher temperature. So, but still I wanted to coat them very quickly. That is what, that means we are not using the bitumen directly. We are using the emulsion to coat the aggregates. Thereby, this is called cold bituminous mixes. So, in the first step, what we have to do is, initially if I wanted to add some emulsion, how do I add emulsion? I will not add randomly. It depends upon the aggregates content. So, how much is the coarse aggregate, how much is the fine aggregate, how much is the filler material. Based on that, we calculate the initial residual bitumen content. How to calculate the residual bitumen content. So, but bitumen content I am talking. Bitumen is actually part of emulsion. So, emulsion is nothing but bitumen plus water plus some emulsifier. So, if I know this initial residual bitumen content, emulsion would be something extra to this bitumen. That is the addition of water and emulsifier. So, if you know the initial residual bitumen content based on this formula, you have to calculate the initial emulsion content. So, this initial emulsion content would be initial residual content by X. X is nothing but the bitumen content percentage in the emulsion. Okay, once if we get the initial emulsion content, we have aggregates. So, first we need to provide some lubrication to the aggregates. That means we add some water. This process is called pre-wetting. So, we will be wetting the surface of the aggregate initially, very light. So, once after getting wet, then we will add the emulsion. Yes. We know that this emulsion already has bitumen plus water plus emulsifier. That means this emulsion already has some water again. Already initially we are adding some water. This initial water one is called as the pre-wetting water content. Okay. This later water content that is present in the emulsion 2. So 1 and 2 together is called total fluid content. But only water 1 initially that we are going to wet the aggregates is called as the pre-wetting water content. So if you come to the optimum pre-wetting water content, because I do not know how much water I should add initially. So for that actually we have two tests to be done. So when I add the water, if that water could able to coat minimum 50% of the aggregates, so we will take the trial. Some let us say 5% of the water we add, we will see. Again we increase to 5.56. So like that we increase the water content and see at what water content minimum 50% of the materials are completely coated. Otherwise, we also perform the dry density. We add some water content, we perform the dry density, we see the density corresponding to the water content. At what water content, density is maximum. So, based on any of these two methods, we determine that water content that we need to add in the initial stages that we call as the optimum water content. So now let us fix the optimum water content. So once optimum water content is known, now we have to fix the water in the emulsion. If that is also fixed, we know total liquid content. So the next step is optimum total liquid content. So now we have aggregates. Now we are going to add some emulsion to that. To the aggregate, we have already added the pre-water content, pre-wetting water content. Now I will add the emulsion. So I will add the emulsion. In that emulsion, let us say some water I have, let us say 6% of water is there in the emulsion. I have added that emulsion and I have calculated the stability, exactly like density. Then again, I increase the water in the emulsion to 66.5%. My pre-wetting water content is always constant because that was determined from the maximum dry density. Now I increase the water content in the emulsion. Again, I have calculated the stability. Again, I have increased the water content in the emulsion, I have calculated. So, at some particular water content that is corresponding to the initial emulsion content, density will be or stability will be maximum. So, then that water content I fix. So, now I already know the maximum water content of the pre-wetting water content and also the maximum water content in the total liquid content in the emulsion. All these two together is called the total liquid content. Now, by keeping this water content as the constant, now we will be varying the emulsion content. Once the emulsion content is varied, we calculate the variation in the residual bitumen content. Okay. So, that is what the final residual bitumen content using which we do the stability, maximum unit weight and soaked stability, dry stability. The values are maximum. Those values we finalize as the mixed design values. So in addition to the cold mix, discussed about the performance based mixed design. So till now, what are the mixed design that we have performed is based upon the volumetrics. So we have those volumetric parameters 100% will not replicate the performance, that is rutting and fatigue of the asphalt mixtures. In order to consider performance-based mix design, there are four approaches. One is in the approach A, this is completely a volumetric mix design like previous one, but one of the difference is after calculating the final OBC, let us say in the Marshall mix design, using that OBC, we also try to cast the samples and perform the rutting and fatigue test, and we make sure that those mixtures will also satisfy the performance criteria. So we are not going to corresponding to the 4% air words. Then here we have more lenience. Not just the OBC, we can have a lenience to increase a little bit of binder content to more than OBC. Yet those binder contents and the OBC check the specimens for rutting and fatigue. Rutting and fatigue. So if the specimens or asphalt mixture could able to satisfy them, that binder content is the final. So in these two, we are still considering the volumetric index design. But in the 3 and 4, so in the 3, usually we finalize the OBC based upon the rutting and fatigue. So we take the aggregate gradation, we add the random bitumen content. First we check for the rutting and then fatigue, then moisture damage. If everything gets satisfied, then we check the mixture for volumetrics. So if that also satisfied, that binder content is the final. But in the final approach D, we don't even check for the volumetrics. We solely design the mixes based upon only performance criteria like rutting and these asphalt mixtures. We have some empirical tests like Marshall and ITS to understand the strength of those mixtures. And we also have the fundamental tests like flow time and flow number. So using which we can understand the stress strain behavior of the asphalt mixture. And we also have some simulative tests where a real wheel will be moving on the asphalt mixtures to and fro. And we observe the rutting over the surface of the asphalt mixtures This actually simulates the field conditions better in the lab, but this is a pass or fail criteria. It will not give any fundamental information about the material. So these are the most of the information about the asphalt mixtures. So in addition to the asphalt mixtures, we have studied about the cementitious materials. Let us say cement is cementitious materials. So how do we produce the cement? Packages are calcium related products, and also silicon related products are siliceous materials. So these products, initially what we do, we crush them, we grind them, we blend them higher temperatures. So once after heating, we make them into fine powder. So when these raw materials are in kiln at higher temperatures, they provide some, they react with each other and they form some compounds. Those are called as the Box compounds. So those compounds are C3S, tricalcium silicate, C2S and C3A, C4AF. These are the four compounds that are responsible for the strength of the concrete. So these compounds, when they react with water, this process is called as hydration. So they release some heat. So and they release some heat. In addition to the heat, they also produce calcium silicate hydrate gel. So this is the gel that is responsible for the strength of the concrete, and also they release calcium hydroxide. So we are not interested or desirable for calcium hydroxide, but we are interested for CSH. So too much of CaOH twice is not recommended to be released during the hydration process. So what are the steps that we are going to do to reduce this released calcium hydroxide, that we'll discuss further. But it also produces more calcium hydroxide, and the citrus also produces less quantity of CSH. So when all these metals are formed and graded into fine powder, we add gypsum to this compound, because C3A tricalcium aluminate, they when they react with water, they lead to placet. That means they become stiff in very quick manner. But we want them to be in the plastic state until we use them in the field. So we do not want a flash set. So in order to avoid that, gypsum will be added so that gypsum stops that reaction. Few tests that we have discussed on cement. One is the initial setting time. Material to set very quickly, and we also do not want material to be set very fastly. And to understand the durability, how it will react with wetting and drying cycles, we also have performed soundness test. And these are the strength test, which is the compressive strength. So we have fabricated a, let us say, tube kind of cement, and we performed the compressive strength. To understand the hydration of the cement, fineness of cement using blind permeability test was also been performed. So as I have discussed previously in the cement, we have already discussed that calcium hydroxide is the byproduct, and if that calcium hydroxide, when it comes in contact with water, that gets dissolved. So in the concrete, if the calcium hydroxide gets dissolved, what happens, wherever the calcium hydroxide place is there, that becomes empty. So porous formation would be possible. That is the reason why we need to utilize that calcium hydroxide. For that, we add some pozzolanic materials like pozzolana, slag, and also some other admixtures. Then those will be hydroxide, and they also will form something called as CSH, calcium silicate hydrate gels, and that will be imparting strength through the concrete. Okay. PQC and DLC design, pavement quality control, which is the topmost course of the concrete pavements. This design includes One is initially we decide target strength for all the concrete mix designs. That is based upon either compressive strength or compressive strength in or flexural strength. So we have two formulas to calculate, and in these formulas, if we wanted to understand the standard deviation, we also that can be determined from these tables. Tables have been given. So once the target strength is finalized, we will be calculating the entrapped air, amount of entrapped air based upon the nominal and maximum aggregate size. So we calculate this entrapped air so that in the total value, we will be reducing this entrapped air so that we know the solid volume. So based on this, the type of the grade that we are going to use, and also the target strength that we have calculated, we can actually guess the water to cement ratio, whether in terms of flexural strength, suggested water content can be determined. But this table is per angular, so if we have some other shapes, we have corrections to that. And what are the minimum cement and maximum cement that needs to be added? That was we have to consider. Once the water cement is finalized, then we also calculate the and aggregates fraction. So in terms of volumes that we do initially the calculation, then using specific gravity we convert them into the weights. So we have done the PQC design. In the similar way in the dry laid concrete also, but here, instead of water to cement ratio, cement to aggregate ratio is more important because this is we are designing for the zero slump. So DLC is just below the PQC, which is having lesser strength than the PQC, and we do not want higher strength to this, and we do not want more plastic state. So cement to aggregate ratio, minimum cement, and we need to calculate the optimum moisture content. So once if you know the optimum moisture content, already we have to calculate the amount of water content. Once that is known, this is for we calculate this per 1 meter cube, but we need to test minimum 5 samples for the DLC. So we calculate the total amount required for the 5 samples, where each sample is 150, 150, 150. And also, in the similar way, various concrete design. In all the concrete design, first step would be this calculation of target strength. So in the pervious concrete design, we need to maintain some amount of air voids so that the water can be percolated or permeable. So we assume some initial water to cement ratio, and void content we calculate based upon the permeability and compressive strength and NMAS. There was a table. So based on that, we calculate the void content. Once if we know the void content and also or low compaction, then we calculate the paste value. Here the main importance in the pervious concrete is paste value. This paste volume is what that is going to be placed on the surface of the aggregates. So we keep changing the paste values, and the highest strength we decide that. Then water content and porous aggregate fraction also can be calculated based on that. So these are the few of the brief discussions on all the chapters that we have discussed, and the detailed discussions on all these topics also are available in the YouTube, which have been discussed in the previous weeks. And this material also will be uploaded, so you can refer to them. Closing the meet.